Hello, everyone, and welcome back to your series of probability and statistics. We were done with one population mean. We didn't do the variance because for one population, usually it's not that realistic or we don't care about it. Maybe we will need to come back later and do the proportions. But for now, I'm going to move to the two population difference in means. Meaning, I have two processes that I want to pick from them, and one of them is claimed to, for example, have larger production or larger output. And I want to see if that's the case. So instead of having only one population that I'm checking against some constant value, no, now I'm comparing two means if one is better than the other. So we call that uh, like confidence interval or test of hypothesis. Both are the same thing, like two faces of the same coin. So we are going to do two population uh, test of means. If we have two populations, we can test the mean, but before testing the mean, we have to find out whether these two populations are independent or dependent. Say, how do I know that? Well, we'll talk about that. But generally speaking, they are usually independent. Why? Because you are getting, say, um, part parts from two different suppliers, and each one is using a different technique or different machines to produce and different everything. So how can they be dependent on each other? They can't, right? They are independent. Common sense would say that. Usually dependent is something you design. You want them to be dependent, and we'll see why would you need something like that, right? You always have to ask questions. We're gonna answer that, but next session. Today, we will concentrate on the independent populations. When you have two independent populations, another thing that is very important statistically to figure out is that do they have equal variances or unequal variances? Hmm, how do you check that? It turns out that usually, well, it's very hard, right? It's very hard to say these two things have the same variance. How would you know that? If I don't know the variance of either, so how can I claim that they are equal? Usually, this is a very high assumption to make, and it's a huge leap of faith. I mean, why would you do that, as we said? Some statisticians would say, run an F test. That's something we are going to learn later to compare the variance of these two populations. Okay. And if you reject, use the unequal. If you fail to reject, use the equal. But then the other side would say, when you fail to reject, that doesn't mean that the variances are equal. It just says that the difference that you've seen is not significant to say with strong statement they are unequal. So let's look at something else. Statisticians have worked out the problem and looked, how critical these assumptions are. So they said, okay, let's take a sample, and we know for sure the variances are two samples, and we from two different populations, and we know for sure they are independent, and they don't have the same variance. Okay, so we checked, say, with the F test, and it failed. So they don't have equal variances, and we run a test assuming they have equal variances. they found that this assumption is very sensitive, meaning if you assume they are equal but they aren't, your answers would be erroneous. You will get far off the mark. And then they did the opposite. They took two equal variances that were equal, and assumed they are unequal and run this test. They found that the answer was not far off. It was closer to the case where if I use both tests, they will produce pretty much the same result under this assumption. But if I use the equal variance assumption and they are not equal, I see there is a huge gap. This one is more precise or less sensitive to this assumption. So unless otherwise mentioned in the problem, we will assume that we have unequal variance, independent but unequal. Okay, so now we are going to compare to see how we can use either one. Of course, you would tell me, why would I use that if I knew that this one is usually better? Well, if you are taking a course, sometimes they tell you assume equal variances, run the test. If you are using calculator or a computer, that's so easy to do. You assume equal or non-equal. We'll see how we do that. So let's start with the unequal, which is the more like widely used. Remember when we had the we were running a test or doing a confidence interval of one population mean, we said usually we are going to use the t. The book will tell you can use the z if you know sigma square, which I never know, or where your sample size is large. And when your sample size is large, that was an old assumption we used to make. Well, it's not an assumption. Yes, if you have a large sample, the z and the t become very close to each other. In fact, maybe when we do the next session of our studio, I will show you, the shape of the T when you have small uh, sample size, medium, large, and we compare that with the normal distribution. And you can see that with large sample size, they are almost identical. Okay. If you open any statistics book, I don't know if we have the T here. It should be at the end. This is chi-square. This is Z. Yeah, here is the T. Look at the degrees of freedom. You start with 1, goes all the way to 30, and then jumps to 35, 40, 60, 120, infinity. So if I take a large sample size, I want to make it, for example, I want to go about 30 because 30 is like when the central limit theorem applies. So if you have uh, samples from another distribution and you say, okay, if they are not normal, but when the sample size is large, I can consider them normal by the central limit theorem, and I can use the z. But if you try to use the t, and let's say your sample was like 32 or 33, you say, no, I'm not going to use that. I'm going to use 31 or 30 so that my degrees of freedom is in the table. Some tables only jumps from 20 to 30, then to 40, and so on and so forth. And you would say, if my sample size is somewhere in this gap, I wouldn't know the t. I cannot interpolate. It's not linear. You can see it's not linear, the equation, the function. So I say, let me use the z because I know the z for any alpha. That was in the old days when everybody was using tables. But nowadays, I can use the t with any number of degrees of freedom. It doesn't matter, right? Because I have a calculator, I have a computer. So unless otherwise specified, I'm always going to use the t, okay? So using the t, remember for one sample, we said t equals x bar minus its expected value, which is mu, over its standard error, which is s over square root of n. Here, instead of having that, I have two of them. So I say x1 bar minus x2 bar minus their expected value. Notice the expected value of a difference is the difference of the expected value, meaning the expectancy is a linear function. So I say minus, what is the expected value of x1 bar? It's mu1. Minus, what is the expected value of x bar 2? It's mu2. Divided by the variance, I'm sorry, the standard error of x bar, x1 bar minus x2 bar. Remember, in the case of one sample or one population, I said it's s over square root of n. But now I have two populations, so how do I find the standard deviation? Notice, we cannot find the standard deviation right from by looking. We have to find the variance first. So what is the variance of x1 bar minus x2 bar? I'm going to leave it for a second for you to think. You can stop the video, and then I will discuss it with you. Remember when we said you find a combination of random variable, the variance of that combination, you assume you are squaring that expression, x1 square, x1 bar minus x2 bar quantity square. And when you square that, you get x1 bar square minus twice x1 bar x2 bar plus x2 bar square. I translate that as the variance of x1 bar minus twice the covariance of x1 bar and x2 bar plus the variance of x2 bar. Independent. What does that mean? Yes, there is no covariance. It's the variance of x1 bar, which is s1 square over n. Notice that's the variance. It's s1 square over n1 plus s2 square over n2. And this one was s square over n. And we took the square root of s squared, we got s. We got n divided by the square root of n. But here, since we have two, I cannot factor out anything because s1 squared doesn't equal s2 squared, unequal variances, right? So I have to say the square root of s1 square over n1 plus s2 square over n2. That's my t. That's the t I'm going to check. And you say, but how many degrees of freedom, right? If you are doing it manually, that's a pain because the degrees of freedom are invariably non-integer value. So you end up with, say, 19.7. You're always going to round down. And we say, just take the integer part and say 19, okay, to make it more powerful. Anyway, so what is that? Do you see the quantity under the radical? We are going to take them between parentheses. So we say s1 square over n1 plus s2 square over n2. Square that. And then divide. You take one part, which is s1 square over n1 squared over n1 minus 1, which are the degrees of freedom of the first sample, plus s2 square over n2 quantity square over n2 minus 1. So it's very complicated to calculate manually. The calculator will do it for you in no time. Okay? So that's how we calculate the t, and mu. So if you want to construct a confidence interval for x1 bar minus x2, I'm sorry, mu1 minus mu2, you say it's greater than x1 bar, oops, bar, not square, minus x2 bar minus t alpha over 2 and this degrees of freedom times this whole thing. This is like times the square root of S1 square over N1 plus S2 square over N2. Okay? And then less than x1 bar minus x2 bar plus T alpha over 2 and degrees of freedom if it's a two-sided confidence interval, or T alpha if it's a confidence bound, times the square root of S1 square over N1 plus S2 square over N2. Notice that this is almost identical to the single case. X1 bar, so mu1 is greater than x1 bar minus T alpha over 2 degrees of freedom times S over root n. Because if I don't have that, and I don't have the subscript 1, S1 square goes out as S, and root n stays in the denominator. So it's the same thing exactly. Or I can check if it's a hypothesis testing. I calculate the T with that degrees of freedom and compare it to T alpha over 2 degrees of freedom and negative T alpha over 2 degrees of freedom, and see if it's within or outside. So I reject or retain or fail to reject. So this is the unequal variance case. But how about the equal variance? So for example, if I can assume that sigma 1 square equals sigma 2 square. In this case, so case of equal variances that we will not be using, I calculate something called the pooled variance or the pooled standard deviation. What is that? I say if they have the same variance, of course, the samples will not have the same variances. So let me take a weighted average of each. Notice that the first variance is S1 square, right? And the second variance is S2 square. So what should I do? I'm going to multiply that by n1 minus 1 and multiply that by n2 minus 1 and then divide by their sum, which is n1 plus n2 minus 2. That's how we do the weighted average, right? I say they are equal. Sigma 1 square equals sigma 2 square, but S1 square and S2 square definitely will not be equal because these are samples. They are randomly selected. So I say, okay, but in reality, they should be the same. And if I select, say, 10 parts from here and 7 from there, I would multiply that by 9 over 9 plus 7, and this by 7 over 9 plus 7, just the weighted average. And that would be SP square, or the variance, the pooled variance. So when I do the T, I say the T is x1 bar minus x, I don't know what I was doing, minus mu1 minus mu2 over SP. Notice SP square, when you take it out, it becomes SP times the square root of 1 over n1 plus 1 over n2. This is SP square over n1 plus SP square over n2. And the number of degrees of freedom is n1 plus n2 minus 2. Why? Because the first sample has n1 minus 1 degrees of freedom, and the second has n2 minus 1 degrees of freedom. So when you add them up, you get n1 plus n2 minus 2. Okay? If you want to find the confidence interval again, you would multiply. You would say mu1 minus mu2 is greater than x1 bar minus x2 bar. Some people call them x and y, so x bar minus y bar, it doesn't matter, minus t alpha over 2 and degrees of freedom. That's the degrees of freedom, and you multiply by SP times the square root of 1 over n1 plus 1 over n2. And this is x1 bar minus x2 bar plus T alpha over 2 in degrees of freedom times SP times square root of 1 over n1 plus 1 over n2. Okay, so that's if you use that. So I got a problem online, can't remember what is it, but I stored it in my calculator. So basically that was uh, two, let me show you what I have. Yeah, these are samples from, I think this was, we were using a special type, not, we were using either, try to remember, I should have written that. I think they were the height of plants. This one was using the current, uh, I can't even remember which book I got. Let me check quickly. Let me see. Sorry for. Did I wrote them? I entered them yesterday. I can't remember. Uh, Influence. Oh, I think it should be here, but I don't know if it's this book or the other book. Hopefully, it's this one. Yeah. Oh, yeah. I remember this was okay. Article of nutrient deprivation improves field performance of woody seedlings. Well, this was in ecological engineering. We were using 10, these are 10 trees. So, and the height in centimeters is given here. So the first one was using the usual fertilizer, L1, and the second one was using a new type of fertilizer that was claimed to increase the size of the plants. So so if I have something like that, notice I'm not going to use the equal variances here. We said we agreed that we would be using this anyway. So what would be the test? My null hypothesis is that mu1 equals mu2. My alternative hypothesis is that mu2 is larger than mu1. Mu2 is the one treated with the new type, and mu1 is the current type. Alpha, we'll use it as 0.05. So we'll be using t equals, or t calculated equals x, well, x, if we want to say mu2 is greater than mu1, I can say x1 bar minus x2 bar, and I'm rejecting on the lower side because that means x1 bar is less than x2 bar. So really, you can write it better as x2 bar minus x1 bar minus mu1 minus mu2, but mu1 equals mu2 in the null hypothesis. But so when we do the t calculated, that would be 0, right? I told you we get that from the null hypothesis, and this would be written equivalently. I can say mu1 minus mu2 equals 0, right? If they are equal, then their difference is 0. So when I do the difference, I get 0. So it's only x2 bar minus x1 bar over um, the the square root of s1 square over n1 plus s2 square over n2, right? And if that's uh, we do x2 minus x1, so that's an upper test, meaning I will be rejecting if this is 5% T alpha, not alpha over 2, all of it is on the side, and degrees of freedom that are very tough to calculate. Well, if I want to do it manually, which I wouldn't, I can go to stat and go and calculate two variance statistics. Okay? I will enter the first one is in list one, oops, one, comma, the second one is in list L2. So if I do that, it gives me S1, SX is 1.3, and it gives me SY, which is SX2, is 0.91. I can use those, and the sample size n is 10. I can divide 1.31 square over 10 plus 0.91 square over 10 quantities. You see how complicated it is? You can do that and find the degrees of freedom, truncate it, and then use the t table, but we can do that very simply by going to stat and go to the test. And the test, I want two sample T. So I will go here. And if I'm using two sample T, I have the data. If they are stored in L1 and L2. So I'm not going to use the stats. Instead of entering the means and the variances and the sample size, I can just use the data because I already stored it. But when I come here, notice this will do L1 minus L2. So I want to use a lower test, not an upper test. If I had stored the first list in L2, so the first list for X2 bar and this one for X1 bar, I'm sorry, X2 and X1, then I leave it as it is. I would use mu1 greater than mu2. But here I want to do mu2 greater than mu1. Notice, mu1 has to be less than mu2. So we have to be careful here which is higher. In fact, if you get a huge p-value, like p-value of 0.8 something, oh my God, I must have done it the other way around. It will tell you. If it's very high, it means you didn't incorrectly, but hopefully if you pay attention, you will do it correctly. Then it asks you, is it a pooled standard deviation? So if it's a pooled, meaning I assume equal variances, I say yes. But you see, the default is no. I'm not going to use that. And then I go finally calculate, and I get t is negative 10.5. Oh my God, that's definitely, I will reject the claim. I would reject the claim that mu1 equals mu2 and conclude, yeah, that the new treatment is definitely much better. It grows, and you can see that from the numbers, really, but at least statistically, it gives you x1 bar, x2 bar, it gives you s1 and s2, and it gives you n1 and n2, and it gives you the p-value. The p-value is so small. Do you see that? It's 6.7 times 10 to the negative 9, which is 1 billion. 6 in a billion. You can find a sample, two samples like these, or even worse. Only 6 in a billion. So you are emphatically saying, yep, of course I know that the new treatment is much better. Okay? So that's how we do it. If you want to run it, well, my p-value is 6.7. So p-value is 6.7 times 10 to the negative 9, which is practically zero. If let's check just for curiosity that we assumed equal variance. Of course, it's still going to reject the claim that they are equal, but would we have a smaller p-value? I didn't run it. I'm just going to, that's what I assume. Yeah, you see, it's 2 in a billion, like 3 times less emphatic than that. So most likely the variances were not equal. If they were equal, you will get a very high p-value, maybe like this or even better, because they are actually having the equal variance. So the assumption was correct. This assumption was wrong, so you wouldn't get the same uh, like rejection power. But having said that, as I said, we are going most likely to use this approach. We'll use unequal variances unless specified in the problem. So, and you can see specifying it in the problem, you only select pooled yes instead of no. They are very easily done. I will show you how we do that also in our studio. So this time I will show you how to read the file. So I will store something like that, maybe this problem, maybe another one. I will store it in a text file, and then I'm going to read the file, run the test out of it, and get the result. Okay? Instead of entering the values manually, it doesn't make sense, especially if it's a large data. Okay, I hope this wasn't long for you. Next time I'm going to discuss the dependent uh, populations and see why sometimes when we design an experiment, we want the populations to be dependent, and we'll see how we do it. Thanks, and see you soon.